Hello students, in the previous lecture we had discussed the type of vector functions. One is constant vector function, other is vector function with constant magnitude, and third is vector function with constant direction. Now we'll derive results based on the three types of vector functions. Prove that f vector t is constant vector function if and only if derivative of this vector function is equal to 0. Constant vector function. The first result is based on the constant vector function. Or another statement of this theorem is the necessary and sufficient condition for f vector ft vector to be a constant is derivative of f with respect to t is equal to 0. Proof. Let's prove the necessary part of this. That is, given is, let us suppose that ft is a constant vector function. So if it is a constant function, so let ft vector is equal to c vector. Same one. Assume. Now this is constant function at time t ft at is equal to c. So f at time t plus delta t will be c. So subtracting first from second, we got f vector of t plus delta value of t is equal to 0. Divided by delta t and taking the limit as delta t equal to 0. So we got definition of derivative is equal to differential of f d raised to t is equal to 0 and proof. If f t is a constant vector function, then derivative is equal to 0. Now, sufficient part is if the derivative of a function is 0, then we'll prove that f t vector is a constant vector function. Let us suppose this vector function in component form. F t vector is equal to f1 t iota, f2 t j, f3 j in component form. Now differentiate this to t. So the first component is second component, third component. So derivative, we are given that differential of this vector function is 0. So this vector function is 0 if all the three components are 0. So differential of f1 t is to f1 t is to t is equal to 0, f2 t is to t is equal to 0, f3 t is equal to 0. Derivative of this function is 0, this function is 0 implies f1, f2, f3 are independent of t. Hence ft, all the three f1, f2 are independent of t means they are constant. Therefore ft vector is a constant vector. If derivative is 0, then if derivative of a vector is to the scalar variable is 0, then vector function is constant function. Now the second part is vector function ft have a constant magnitude. It is constant magnitude but variable direction. Then variable direction if and only if ft vector dot derivative of ft vector dt is equal to 0. Now again we'll prove both the parts. Given ft is a constant vector function with constant magnitude. When will this be constant magnitude? Definition of constant magnitude means if and only if modulus of ft vector is equal to constant. Say that's what is equal to c or c basically. Now f vector modulus square can be written as f dot f modulus square f dot f is equal to c. Now differentiating both sides to scalar quantity t time. So this we got scalar product is commutative. So this is written as constant is equal to 0. So f dot twice of f dot df dt is equal to 0. Dividing by 2, we got different left f vector dot df vector is equal to 0. So if f has a constant magnitude, then f dot df dt is equal to 0 henceforth. Now third part is a vector function ft have a constant direction but variable magnitude. When will this happen? If and only if f cos of derivative of f is to be equal to 0. So constant direction. So let us assume that this f is equal to magnitude is variable ft and direction is capital F vector, where F is a unit vector in the direction of F. Now differentiating this vector, this is derivative of differentiating it first is to time. So d F vector dt equal to product first function, second adjective, first adjective, then second function. Now multiply by F vector both sides, cross multiplying cross multiplying vector. So this is the quantity, cross vector this is equal to F vector t, d F dt, F vector F cross F 0, F F vector F t F t F square, F cross d F dt. So we so F cross d F vector dt comes out to be this is 0 F square F vector cross df. Now, now we'll put the first one, necessary part. Necessary part is this. Given is f has a constant direction. That is, f is a constant vector. So differential vector is equal to first result. First result. Therefore, f vector capital F is to be equal to 0. So third and fourth implies f vector cos df will be equal to 0. That's true. Now, substitution part is given that f t vector cos d dt of f t vector is equal to 0. So using third, you know that this is equal to this. So replacing the value, substitute this from this first third. Using third. Now for this to be 0, this is a variable quantity, so this must be equal to 0. So this will be 0. Got f vector cos df vector equal to 0. Since f is a constant magnitude, so you go second result, use the second result, f vector dot df equal to 0. So fifth and sixth implies df dt must be equal to 0 for the dot and cross product of two vectors 0. F is a constant vector, so for this equals to true, df dt must be equal to 0. Must be 0. Therefore, f is a constant vector both in magnitude and direction. Equation first implies this is a constant vector.